diction part that I have suggested. Okay, so yes, I will record this. All right. So how in the world should you go through about solving this? Let's go ahead and pull up idle. And I'll start by giving you an outline over here. Okay, because again, you've got a week to solve this one, and I'd rather give you the tools rather than have you, you've all had the lab on it, so ostensibly you've all had time to look at it. So I'm going to call it Hawaii or whatever. Okay, and now what I'm going to do is I'm going to, it's over here so that we've got it. Okay, what we're going to need now, this is coming with the dictionary one. So obviously the solution I recommend uses dictionaries. You don't have to use dictionaries, but boy, will it make your life easier. Okay. So specifically what you want to do is create 2 dictionaries, for one for, you can have 3, one for consonants, but the important one is one for vowels, which takes in basically your vowel key values. So your vowels are your single vowels. So for instance, A to E to and so on and so forth. I'm not going to type out the entire chart for you. I just want to basically begin to populate it. The second thing is that you want to have a second combination for double vowels. Basically, and this is for where you have those rules for pronouncing 2 at once. This is generally the easiest way to do it because you kind of group them either singularly or double. Okay, and the key here might be like, again, the one we were doing is EI for goes to A, and let's see, I think another one was AU to go to OW, right? So again, I leave it to you to populate that one fully. And don't worry if you're furiously copying this down. I'll try to send it via Discord, drop it on Discord, or I'll send it out an announcement or something, But overall, you have 2 big tasks here. One which is easy and one which is the more difficult one. So we should separate, but regardless, we should separate them. One is, I'm going to call it validate, which given, I'm going to go call it text because, actually word. Given a word, I want to tell whether or not it's a valid word in a valid Hawaiian word. Given a word, tell me whether it's a valid Hawaiian word. What I'll do is I'll assume it is, and then I will disprove, and then I'll attempt to disprove it, right? And the way we can disprove it is fairly easily. Go through every single one of the characters in the word, right? And if that character is not in, so what we can do is say, hey, for letter in word or for character in word, if letter, and then whatever we need to do is you'll need to complete this is not valid, is not a valid letter in Hawaiian words, right? Okay. So, and then I'll just put in, I will just simply make sure that it will compile, or sorry, run, even though it doesn't really work correctly right now. I'll put in a pass right here. Remember, pass just means, yes, I put in an indent and it's expecting some indented text in order to keep forward and not have a syntax, keep moving forward and not have a syntax error. So let's put finish over here. And this one, again, is all the rules for that are basically the 12 letters we want to use plus the apostrophe, The other one we want to do is def pronounce, and I'll just call it pronounce because pronunciation is a mouthful. Okay. And yet, given a word, a valid Hawaiian word, give me the pronunciation for it. Here we can assume that we would run it through validate first. So it would be a valid word. Now to do this one, what we'll have is that we'll have some output. We're going to do basically our accumulator pattern again. So output will be what we're doing, simply because we output it, and it's also easier to spell than pronunciation. So again, it's kind of that readability versus intent thing. So what we're going to do is that we return the output at the end. Okay. Now, again, what I was saying earlier, in case you didn't catch that, is that the mistake you don't want to make here is as follows, which is for letter in Word. We did that up above, but that's useful if you want to look at one letter at a time in sequence, in order. Here we don't, though. What we want to do is that we want to look at every letter and also look at the letter after it. So here what we want to do is kind of look at the, you know, one letter at a time, but we care about the index because we need to look at the next letter. So you might think, okay, let's do for I in range. Don't type this out, by the way. Range length word, right? Where we go through each of the valid indexes. But again, this will advance each index one at a time. This is the appropriate approach if you're like working in C, because you can modify I in the in this function. But in Python, that's not really what we want to use. It seems a bit counterintuitive, but what we want to use is a while loop, oddly enough. Okay, and the while loop is going to be like we'll say I, where I is the index, I is equal to 0. I is the index, while I is less than the length of the word. In other words, while it is not past the last valid index, we want do stuff. And the reason for this is because what we're going to be doing when we look at each letter to get a pronunciation is that we're going to be reading, we're either going to be reading one letter at a time, or we're going to be reading 2 letters at a time, right? So if the vowel, for instance, if it's a consonant, obviously we're just going to read one letter, right? If it's a valid consonant, we're just going to read one letter. If it's a double vowel, however, we're going to need to read 2 letters at a time. And what we'll need to do is we'll have to increment I by 2. Make sense? So what we need to do is work on looking ahead, essentially. So the idea here is like, we want to say, okay, if word I plus word I plus 1. Okay, so for one instance, one way we can do this is like say, if word I and I plus 1 is in double vowels. This is like the first check you probably want to make as you're reading. What does this do? This says if the current letter I am at and the next letter, the one to the right, I plus 1, if we concatenate that together, so say again, I'm at E, I've got an E, and then after me is an I. If that is in double vowel, what does that mean? If this is in this dictionary, then that means that this is a double vowel I want to use, and I should add that value to the output. Make sense? Elif, well, if it wasn't a double vowel, maybe I should check if it's in the single vowels, right? Make sense there? And then you do the same for consonants, or if it's an apostrophe. There's some annoyance you have to go about with W's, but but when you hit a W, you know that can be the case. So you can set that up accordingly. But the idea here is that what we want to do before we do anything is check to see, okay, we've got this letter and I've got the next letter. Let's see if it's in a double vowel. if it's in this double val. What this in statement does is that it checks, is this two-letter combination in the keys? Is this, so again, if it's EI, it will say, aha, EI is in the keys. It's one of the ones on the left of a colon. So it's a valid two-letter double val. And so that has an appropriate output, and we can get that output. Make sense? This will probably make more sense as you're going through it, but trust me, this makes it a bit easier. Now, that being said, there is a bug I did introduce right here. Any guesses as to what it is? Well, if we look back, yes. Yep, I can get an out of bounds error. For instance, if I go back to our test word K key, right? It will go, okay, this is a consonant, go to the consonant and translate it appropriately, or just simply output it. EI, then we go, so we increment +1 at that point to go to I is equal to 0. Sorry, I is equal to 1. At I is equal to 1, we check index 1 and 2 and concatenate them together. We see, aha, these two things go together. So then we get that appropriate output. So we go, so that gives us, that gave us K, and now that gives us A and a dash. And then we I +2 there because we want to read 2 letters ahead. Since we already read I, we don't need to do that. So we jump from index 1 to index 3. Then we output a K. And then when we get to I, that's where we get our issue where we say, okay, I'm going to look ahead at I. I'm going to go to I, which is the, so I'm going to get the, what's at index 4, which is I. And then I'm going to look at index 5, but there is no index 5. So we get an index out of bounds exception. So do we have to put him? So this is one of the areas where, even though we had an issue with Python giving us trouble with the previous, with not being able to use a for loop the way we wanted to, this is, again, one of those areas where Python really is awesome for us. Because what we can do here is that we can abuse slices. What do I mean by that? Well, with slices, we can do something like this. So for apple, right, let's go ahead and say word is apple. Right, we've learned about slices, and we've simply say, like, we can do from, if we want to say word from the beginning to up to, but not including letter 3, we get app, right? And then if we say 3 to the end, that gives us index 3, which is 0, 1, 2, 3, up to, but not including, is up to and including the last characters, ill. So the question is, what happens if I slice something like this? 3 to index, why don't we add a few more zeros there? What happens there? Oh, it gives me unterminated string literal because I accidentally hit the single quote as I was hitting enter. How embarrassing. Okay, so I enter and it gives me LE. Interestingly enough, you don't get out of, I have no idea why this is, but I am sure going to use this to my advantage. You don't get out of bounds errors when you do slices. How useful is that? Why do I mean that? Because I can just change this into a slice now. I can say, let me look at this character and the next character, and it will no longer be out of bounds. So we want to change this to a slice. And what you have to put there, I'm going to leave up to you. It's, just you're trying to read 2 at once. It's just that you want to make sure you're doing your slice math right, because it goes up to but doesn't include the index on the right side. Okay, so now, else if consonant. So again, this code is not even fully done or something like that, but that's kind of the idea here. That helps if you use dictionaries. If you aren't using dictionaries, then you're gonna have a lot of nested if statements, and it's doable, but it's worthwhile to figure out this kind of way of doing things. Once you have your validate working and you can validate a word and you can correctly pronounce a word, that's when you can kind of combine them together for the loop, which is actually a relatively easy part, which is just simply asking the user to enter a word and then asking them again and then again until they say they don't want to do it anymore. Okay, make sense to everybody? All right, any questions on this before I move on to whatever my next topic is going to be? Yes.
How do you deal with when W is like, how do you deal with the weird things with W?
So with W, you can use so let's see, with W, I think you can use a similar thing where you can check if it is what the previous letter was by slicing again. So you can check the previous index. Again, if the that is something I would move forward. So what is the apostrophe exception? Do we have for an apostrophe? Is there anything? Yeah. So for an apostrophe, okay, an apostrophe you treat like a consonant. Interestingly enough, all you do, but that's a great question. So apostrophe, you do whenever you see an apostrophe, just treat it like a consonant. The issue, you might have to deal with some weirdness having to do with hyphens around it. But again, like, yeah, so spaces and the apostrophe are valid as well. But that's something you can craft. But essentially, if you see an apostrophe, just output an apostrophe. If you end up with dashes surrounding it, you can always replace dash apostrophe dash with an apostrophe, with just a single apostrophe. Or you can just simply say, okay, I see an apostrophe, let me remove the previous dash and make sure that, and not output a dash after me, which is fairly easy to do there because not doing something is easy there. But again, the apostrophe, yeah, just treat it like a consonant at first until you get to a point. Again, the test word for that for apostrophe would be humu humu nuku nuku apua, where you want it to, where you've got ah right over here. So you want to do ah right over here. Notice that you've got the apostrophe in between, where that just has it doesn't have a dash after it. I would work with the things like the W and the apostrophe, get everything else working first. It's easier if you've got the right framework for it. If you use the suggested framework that I have for this, it's easy to go and patch in those exceptions. At least that's been my experience. Any other questions? Because those were good questions. Yes.
It's always like a vowel before the W. So you put check if it's in the vowel. Like you just put like AW, EW, OW, and then like check if it's in vowel and print like what outside in that clip.
I mean, it like editing this thing. This one over here, or double vowel. I mean, you could try that, sure. I haven't seen it done like that, but I don't. And you might have to program around that, but I don't see why not off the top of my head. Any other questions? Sorry? I will. Let me go ahead and do that right now. Do. Okay. And now I just have to go to the appropriate out of 1.5 million channels that I'm subscribed to. All of which that I use my real name for because I'm a weirdo like that. Okay, that's another great question. Is the exam this week? No, it is not. It would be next week. All right. So in other words, you would get, I would say your next, I'm planning on giving the exam, and it will include up to file reading, but not dictionaries. It will be the 31st and the 3rd appropriately. So, sorry, 31st and 3rd as appropriate for your section. If you need, again, and if you have any issues with that time, please let me know. but I plan on dropping in a practice exam on Thursday so that you have plenty of time to review for that. And then next Thursday, I want to definitely use I want to definitely reserve as a review session for that. Okay. So let me go ahead and check what we have here. So we have Hawaiian, so that was Hawaiian pronunciation. And now what we're going to be talking about this week is also Monte Carlo approximations and cheating at statistics. So for Thursday, what I want you to do, rather than, I don't have lecture videos like normal. Instead, nor do I have like stuff from the textbook explicitly, other than a textbook exercise we'll be working on Thursday. What I want you to do is watch these videos that I have dropped on you over here, which is, oh yeah, and I have to remove those references to quizzes. Those quizzes don't exist. Those were for an old incarnation of the class, but the videos are still valid. So this one is all about something called the Monty Hall problem, which you can prove via statistics. But again, like if you prove something, and again, so Monty Hall problem, and I'll go over this on Thursday in detail, but note that, like, again, dealing it with about it with statistics, talks about uniformly at random. I was expecting some like expected outputs and stuff like that, but that requires us to do math. Monte Carlo approximations, on the other hand, don't require us to really do math other than counting. Basically, well, did I win the game or did I lose the game? Okay. This is an actual idea of a Monte Carlo simulation going on over here. And here's a kind of Monte Carlo approximation being applied to carnival games, basically saying, okay, so what is the chances that somebody wins like one of those ring toss on a bottle games, right? You can't really approximate, figure out the statistics for that with like, okay, here's, how people throw stuff, here's how it typically lands and stuff. You can't. So with like games like that, where they rely on too many variables to figure out statistically what the outcomes are, what do? You count the number of people who win versus the number of people who lose. Or count the number of winners out of the total number of people who played, and that will give you your, the more people you watch, the more accurate of a win rate you'll have, or an idea of the win rate you'll have. We'll be talking a lot about gambling in these upcoming episodes, in this upcoming not episode, but like lectures, because those are typical, because games of chance are very exciting to like look at and see, okay, what are the outcomes for this? There's also, again, I'll display a couple of different games of chance that are presented to people as though they are fair games, but they're not. Typically, that's one of my test questions typically for exam 3, which is, here's a game of chance. I say it's fair, but because it's on the exam, it's not fair. So let's write a program that calculates the real odds to the game. Now, the other thing I should mention about the upcoming exam is that it's a lot more open, I'll say. I'll try to make it a lot more open in the sense that you should be able to use your code, your laptop to write some code, to write some programs. So, I'll say, write a program that does this, and you can use your program, use your IDE to actually write that program and double check to make sure it's working. So I'm going to give you a couple of just kind of heads up that you would not expect about that, because it sounds like I'm giving you like something great, like having an open book stuff. It doesn't mean that my questions are going to be harder. That's not what I'm going to say. My questions are not harder. What happens is that it takes you longer to write it. It doesn't seem like it would. Like you think, okay, if I've got an IDE telling me I'm doing this right or wrong, I'd be able to do this fine. But that's the thing. If it tells you you're doing it wrong and you can't figure out why it's wrong, suddenly you waste like 5 minutes trying to figure out why it's wrong. And that becomes very difficult. So again, your code doesn't, if you can't figure out what's going on, your code doesn't have to be 100% syntactically correct for your answer. If I can see that you've got the right algorithm, that's what I care about. for what you're doing for those questions. All right. So questions about dictionaries in general? No, or do people feel like they've got a solid grasp on dictionaries already? Yes, no? Because otherwise I could just, jump in and do the exercise we were going to do on Thursday today. Sound good? All right. So why don't we go ahead and talk about Monte Carlo approximations in general? Okay, so over here, I'll go ahead and drop this in chat for, okay. Yep, again, I've got to fix that link. I thought I went through like at the beginning semester and fixed these links, but apparently I just like forgot to hit save on all of them, which is annoying. So if we go to our textbook and we'll go and open this up, this will give us, so yeah, let's go ahead and go to our textbook, Runestone Academy, and if you go over here, you can either go to Canvas and click on that link that I just fixed, or you can scroll all the way down over here on the page and go to exercise 12, which says it requires files, but we're not going to use files to solve what we're doing over here. Okay. Instead, today, what I'm going to talk, and we'll work on this both, I think, today and tomorrow, because approximating pi, we'll see how much time we have for that. That one's a bit more of an abstract one with Monte Carlo simulations. Instead, I do like to talk about the Monty Hall problem. Okay, so yeah, I'm like, went over dictionaries. Don't really need to go over here. So the idea here with, remove the Monty Hall reference. Okay. So for those of you who aren't aware, there used to be a game in the 70s called Let's Make a Deal. And that was run by Monty Hall. And there's a question, and the idea here is that basically you'd know you'd be getting some prize, okay? You'd know you'd be getting some prize, but then Monty would go, well, do you want this prize or do you want what's behind the curtain instead? Do you want the definite thing in front of you or do you want the mystery item instead? Which might not be, it might be better. It might be, it might be worse. And the idea here is that you've got one big prize and there's two doors that will open. So you've got three doors, you choose one, 2, or 3. He'll open up the other one and say, okay, now that you've seen this one, do you want to switch to if you've chosen door 2, he might open door 3 and say, now that you've seen what's behind door number 3, do you want to switch to door 1? Or are you confident about what your choice is? Okay. Now the Monty Hall problem, now in general, we don't know. Because it depends on what's behind the doors. But now let's posit that we do know what's going to be, what the possible pile prizes are. That's what the Monty Hall problem is. Okay, it's a brain teaser, the idea here. And this is what was sent to Marilyn Vosavant's Ask Marilyn column in Trade Magazine. Okay, suppose you're given a game show, okay, and you're given the choice of 3 doors. Behind one door is a car, and behind the other 2, goats. Okay, you've got cars, you've got goats. Now, there's an unwritten assumption in this puzzle, in this brain teaser, which is that the car is better than goats. And my wife would probably strongly argue that the goats are the superior option. They're very cute. So you pick a car, so you pick a door. So you've got 1 car, 2 goats. You don't know what doors they're behind. And you pick, say, door number 1. And the host, who knows what's behind the doors, opens another door. Well, in this example, 3, and he reveals, there's your goat. There's a goat over there. And he then says to you, so do you want to pick door number 2? Do you want to switch? And the question is it in your advantage to switch? Okay. So he opened up the door. He says, it's a goat over here. And he always will open up to reveal a goat, in case that's clear. So there's 2 goats. You pick your initial one, and he'll always open up to reveal a goat. Now, here's the interesting thing. Vos Savant, very smart woman, she said that that the consistent should switch to the other door. And that, in fact, it's superior to switch to the other doors. You might be thinking it's a 50-50 shot at that point. But Marilyn says it's not. It is in fact, if you switch, a 2/3 chance of you winning. Whereas if you stay with your initial pick, it is a 1/3 chance of losing. This is one of those very famous things in statistics because it seems counterintuitive. In fact, it is so counterintuitive that many readers of Vos Savant's column refused to believe that switching was beneficial and rejected her explanation. After the problem appeared in Parade, approximately 10,000 readers, including nearly 1,000 with PhDs, not sure how many of those had math PhDs, wrote to the magazine, most of them calling them wrong. Even when given explanations, simulations, and formal mathematical proofs, many people did not accept the results that switching was the best strategy. Paul Erdos, who's one of the most prolific mathematicians in history, so much so that just like actors have a Bacon number, which is how many degrees of separation are there between acting in a movie with Kevin Bacon, people who work in this field have an Erdos number, which is how many degrees of publication are there degrees of separation are there between you publishing with Paul Erdos. Mine is 5. So, which is actually about average for anybody who actually has an Erdos number. And if you happen to have both, you have a Bacon Erdos number, which is very interesting, very limited. So one of the most prolific mathematicians in history, he was unconvinced until he saw a computer simulation showing that this was correct. Now, for those of you who don't understand why, that's okay too. I was like, what? How? It's just 50-50 because there's 2 options. You either win or you lose. But it has to do with the fact that you get information gained from doing this. From the fact that what happens is that the door gets opened up and suddenly there's information revealed. Okay. Let's think about this for a sec. Your initial guess, okay? If we just simply made a blind guess and no doors were revealed and we didn't have an opportunity to switch, our chance of winning, there's 3 doors, it would be 1 in 3 chances, right? So the idea here is now are we betting that our guess was right or wrong? Okay. Let me go ahead and show you what I mean by ad absurdum. Okay. Suppose instead of 3 doors, we have 1,000,000 doors. I picked door number 1. Monty here opens up 998,999 other doors and reveals all the goats and the horrible smell that probably accompanies them with that many goats in one area. So, and he says, okay, do you want to switch or not? Now think about it. Was your 1 in 1,000,000 shot right? Or is it wrong? That's what you're guessing there. In fact, we can see this flow chart right over here, right? And there's this standard assumptions that work here. The host always opens a door that's not been picked. The host always opens a door to reveal a goat and never the car. And you have to have the chance to switch between the original door and the one that leaves open, right? Here is your initial configurations. The idea here is that we have 3 possibilities. There's 3 possibilities, right? For what's going on here, for our initial guess. We choose a door and the goat's behind it. We choose a door and the goat's behind it, or we choose a door and the car's behind it. In case 1, where we chose a door and the goat is behind it, and the goat's behind it and the car is at like this location, door number 3, Monty will reveal door number 2. We switch and we win. Door number 3, if on the other hand, we pick door number 2, we pick a goat. We pick door number 1 and the car's behind door number 2. Again, he opens up door number 3, we switch and we win. On the final iteration, right? What if the car was here? What if the car was here? What if the car was here? We pick door number 1, the car is there. He'll reveal a goat. If we switch, we lose, regardless of which goat he opens, right? So in 2 of the cases, our initial guess was wrong, so we switched the winning guess and we win. And in that third case, switching was wrong. Switching was the wrong choice. There is, it is one of those things that takes a bit of time to kind of, think about. But again, it involves statistics and logic, and that's hard. And sometimes and also like it's Tuesday on what? Is this week 9? Yeah. You're tired. You don't want to think about this stuff. So instead of thinking about it, the idea here is with Monte Carlo simulations is that stuff is difficult. Let's instead figure out let's go ahead and write a program that simulates this game based on and then we can check which strategy we're using. Okay. So the idea here is that I've got the way I typically work these things is I provide you some game, and I'll create a function that has this game, and I'll return whether I won or whether I lost, typically a true or false value. True if I win, false if I lose. Okay. For this, and almost always in all this, I will need to import random, okay, in whatever I'm doing. And the reason is that I've got some, I've got some goats that need shuffling around. So let's go ahead and create a doors variable. That's going to be represented by a list. And the idea here is that I'll have a car and a goat and a goat. Okay. We can call them goat 1 and goat 2. It doesn't really matter which one we do. But I'll just simply call them goats, or G for goats, simply because the outcome is the same regardless, right? Whether one goat versus another. Now notice I put them in this order, C, G, G. Obviously, if I played this game every single time, it wouldn't be the same way. It wouldn't be interesting. So instead, what I'm going to use is I'm going to use a function built into random, which is super useful, called random.shuffle, which does exactly what you think it will do. And right here, I'm just going to temporarily print out doors to kind of show you that it does what we think it does. Print doors. Okay, and so what goes on here is that we run game and save and run. And yeah, let me go ahead and there, right? I can full screen there, and that makes it a bit easier to see. Save and run. And we notice that we get that the C hops around a bit, right? And if I give them, G1 and C1, we can see that those other goats hop around a bit. When I just have G and G, it's hard, you can't tell them apart, right? They're the same. So I'm just going to keep them G and G. But the idea here is that random will do exactly what you want it to do. Given some list, it will take everything in the list and put it in a random order, which is useful for what we want to do here. Now, the idea here is that we want to we need now pick a door, then we need to reveal a door, or then we need to work through the logic of what happens after we reveal a door and want to switch versus if we want to stay. Okay, so here, what we need to do is that we will pick a door, and our door will always be our choice will always be the first door, because statistically there's no statistical difference between us choosing the first door, the second door, the third door, right? They're all the same statistically speaking. Just always choosing the same one makes it a bit easier to program. Okay. So, and my idea here is now what I'm going to do is that I am going to simulate what happens if I were to, perform the switching strategy. Okay. So Monty, I choose a door. Monty's going to reveal a door. And then I switch. So if choice equals C. If door 0, right, was or rather I should say, we can go ahead, if door 0, if my choice is a car, right? If I initially chose a car and said my initial choice was toward door 0 and my strategy is to switch away from it, I'm going to lose no matter what, right? If I choose it, if I initially chose the car, I just lose. Return false. I did not win because I will switch away from it. No need to code that any further, right? On the other hand, else, if car, so if, and honestly, I could just simply go on, just simply leave it at there, but I'll go ahead and make it a bit more realistic and say, hey, if, let's see, let's go ahead and do elif instead. If doors 1 equals if door 1 is the car, door 2 is revealed as goat. So in this case, now we swap. Choice is equal to doors 1. And then we do the same thing over here, where if the car is behind door number 2, if the car was behind door number 2, we revealed door number 1's revealed as a goat, and now we swap. And then if choice, in fact, we can just, I will go ahead and just rearrange this actually. If door number 1 has the car, if door number 2 has the car, we swap. Otherwise, actually, yeah, we need that there. Sorry, I always think about doing it a different way every time I do it. So now if choice, so yeah, if we initially chose a car, we're going to swap away from it, which means we lose. Yep, we can just simply say that. Otherwise, if we didn't choose a car, if we chose something and it was initially goat and the first thing is a car, we swap to that one. Otherwise, we swap to the other one, which should also be the car. And if choice equals car, return true. Okay, and then, so now what we can do is that we can print the outcome of this game, and we'll get either true or false for running this game. Okay. Okay. Oh, I get none, false, none, false. Okay. So print choice is equal to choice is equal to the car. Oh, no, right there. I forgot to switch that one. So we either get true or we get false now. Okay, so unfortunately, me clicking it doesn't really do us much good like that, because that just gives us true or false, doesn't really give us pertinent information. So what we're going to do is now we've simulated a game, we're going to do our Monte Carlo approximation. Okay. And the idea here is that this is named after, it is a coincidence that is Monty Hall and Monte Carlo, I should say, a very fun one. For those of you who don't know, right, the idea here is that if we go to maps, right, Monte Carlo is located here in Monaco, which is one of those interesting microstates that just are one of those that that Europe is just littered with. Well, not really, but it's got, because that implies something like gross, but I mean, it's just got a lot of, there's all these interesting little tiny countries. Monte Carlo Casino in Monaco, which is a well-known gambling thing. Before I move on, like when I say littered by the, it's located right here, you know, of between Italy and France. France has a number, you know, located, it has a number of small states next to it. You're probably familiar with Luxembourg and Liechtenstein, but those are actually fairly large when you compare it to, say, Andorra, which is ruled by, which the government has co-princes, one of which is always the president of France, I believe. So again, it's a really interesting kind of deal there. There are all these kind of little countries out there, and it's worth your time visiting if you have the chance. But Monte Carlo is known for the Monte Carlo Casino. I mean, again, it looks like a very rich area, and it is. I mean, this kind of screams high-end luxury, right? The idea here, though, is that if we walk into this casino and see a bunch of games of chance being played, as I was describing earlier, we may not know how to figure out what the odds are, right? What are the odds that I win at a table of blackjack, or at a table, you know, or a game of Texas Hold'em, you know, and what are my odds of winning? And the answer is you have no idea to reasonably calculate that right now, unless you sat down and knew the rules of the game inside out. But if you don't know the rules of the game inside out, just watch how often people win and lose. Keep a tally of how often people win versus losing. And if you watch enough people, you will get close enough to the true answer. And that's what we're doing over here. We've stated that mathematically the outcome of this game, see, the outcome of the Monte Hall problem is that if you swap, you have a 2/3 chance of winning. So now we'll put that to the test by actually playing that game. So I will create a variable called trials, and I'll say there's basically, and I'll set that equal to 10,000. That's how many games we're going to run, because this thing can perform games and do these simulations like nobody's business. And we simply do is say for in range trials, we're going to play the game. We're going to need an accumulator. Now, I have it all capitalized, so that not because I'm trying to shout trials at you, but because because I want to indicate that it's a constant, that basically it's something that I'm going to be using, and I should not change the variable in the while the program is running, right? I shouldn't like increment it or decrement it or anything. So wins is equal to 0. And what I do is I simply say for this, outcome is equal to run the game, store the outcome. If outcome equals true, and I will simplify this actually, I can cut this down quite a bit, then wins plus equals 1, right? If I won the game, so I play the game. If I got a true back, that means I won it. Increment my wins. Otherwise, I don't need to keep track of the losses, because I just need to keep track of the wins and the number of games that have been played total. And because now I can calculate what my win rate is, which is print wins divided by trials. Now let's go ahead and cut this down actually to like one. I need to prove a point here. Let me go ahead and run it once. And it says I have a 100% chance of winning. I've only observed one game. Obviously this is wrong because I've only observed one game. I don't have enough sample size. I haven't seen enough games to be played. That's something important in any kind of scientific study or scientific observation you do, that you have enough of a sample size. Similarly, 10 doesn't really give us quite enough data either. It tells us we have a half. It's all swingy. Look at how different. It says we have a 70% chance of winning, a 60% chance of winning. We've seen 80% chance of winning. We've seen a 1% chance of winning. Yes.
We can see
Sorry. Sorry about that. We see a 1% chance of winning. Oh, this is so vexing. I'm trying to figure out the best way to. Oh, give me a second. Boom, boom, boom. Okay. There, I'm running it now. And we can see that it is a swingy win rate. With I'm only doing 10 games. I've seen sometimes I win 90% of the games. And sometimes I've won only 10% of the games. So obviously we need more trials to get an accurate result. That's why I kind of put in 10,000, because if we put in 10,000, we start the more you have, the less swingy your results are going to be. Right over here, as we see as I run it now, it's always around 66%, 67%, 66%. I've seen I think I saw a 68 earlier, which is very, there was a 65% just there, but it's around 66%, which is about 2/3. And the more of these digits we add on, well, this will take 100 times as long because I added 2 digits. No, I added 3, so it'll take 1,000 times as long. Uh-oh. Oh, well, let's go ahead and see. Now that I forgot, it does take a while for it to run and it will lock up the screen. And don't worry, it'll crash in a couple seconds anyway. There we go. Time limit ran out. So let's go ahead and go to 100,000. 100,000 games gives us a very good result. And we can switch, and this is the strategy for switching. And if we change the way it works, which is that instead false would be winning, which is the strategy, what would happen if we stay, right? If we initially chose if we do the stay strategy, which means trust our initial check, sorry, trust our initial guess, we'll see that if we run this, that we get only 1/3 of a, 1 in 3 chance of winning. This is kind of the power of being able to approximate these games. Okay. So now on Thursday, I'm going to go over I'm not going to go over the thing in the middle. It makes a very good project though for kind of thing you want to do, which is predicting stock prices. But the idea over here for on Thursday, I will go over approximating pi, right? But I want to leave you with a game to kind of think about before Thursday, okay? And the game is as follows, right? The idea here is that we're going to play a game, a betting game, and involves cards. And what I've got is I've got 5 black cards, which will be represented by B's, and 2 red cards, okay? And what I'll do is I'll shuffle them and turn them face down. Okay? And the object of the game is you win if you can flip over 3 cards and none of them are red. Okay, you win if you can pick 3 cards that aren't red. I mean, your odds are pretty good, right? I mean, there's only 2 red cards. You only have to pick 3 of them. I mean, that leaves 4 cards on the table. And half of those cards are going to be red. Right? I mean, it's pretty good. Every time you choose a card, right? It's like 1 in 7 chance of you've got 2 in 7 chance of losing, a 3, then a, what is it? A 4 in 6, sorry, 2 in 6, and then a 2 in 5 chance. So it's not, so each time you have a more than 50% chance of winning. So obviously your chances of winning are greater than 50%. Right? The answer is that we are all suckers when we want to win. When we want to win, it's just if we see a bright object and we see a chance of winning, a game and it seems like easy money, we're going to take it. But this is not easy money because the chances are because the part because the lie right there was subtle. I said your first one, it was a lie by omission. I said that your chances of, right, when we pick up a card, right, any one of these cards, there's a 5 in 7 chance of us winning here, right? More than 50% chance. When we get the next card, there's only 6 cards left, right? And 4 of those cards would be black. Well, 4 is 6 chance of winning. And so if I've chosen 2 black cards, then the next is that I've got 5 cards, 2 of which are red, 3 of which are black. All of those chances are, each of those in turn is a 50%, is more than a 50% chance of victory. But the lie is by omission is that the fact is that I'm presenting these as though they are independent chances of winning. In fact, they are what we call dependent variables. These are not independent rolls. In order to win, you have to win all 3 of these checks. And anybody who's played an RPG or a tactical game where the chances where you have like a 10% chance of missing knows how often that 10% chance comes up. Anything that requires kind of accuracy or luck base. If you've played Pokemon, you know that your fissure never hits. Your one-hit KO move never hits. But the enemies will always hit and knock out your Pokemon. Just the way it works. Right? You've all played that where your luck is terrible, but your opponent's lucks are great. Keep that in mind when you're looking at these. But the idea here is that these are not independent things. They're dependent. So in reality, the chances of you winning is multiplicative of these fractions. It is 5/7 times 4/6 times 3/5 because they are all because that is how you calculate this kind of thing. You multiply those chances, which let's see that on the top, that is 5 times 4, which is 20 times 3, which is 60. Out of 6 times 5 on the bottom, which is 30. 30 times 7 is 210. 210. Let's remove those zeros. 6 and 10 doesn't sound that good, and we can divide by 3 right there, right? The chances of winning are it's so weird. Your chances of the opponent's chance, your chances of winning is 2 and 7. Is not, which is the exact opposite of what you would think, right? You'd think I'd never have a 2 and 7 chance of winning. I have a 2 and 7 chance of losing, or something like that. But no. And this is the way like these kind of scams can work. So this is one of the games that we will explore, or these games of chance that we'll explore on, and we'll do a Monte Carlo approximation to kind of show this, because again, how are you supposed to know that you just multiply this, right? Your odds, and again, you're tired. How can you keep track of these odds in your head? So how are you supposed to know to multiply these odds together? Unless you've taken a stats class, and the answer is you don't. Instead, what we do is that we make a program that simulates this game and see how often this works. I'll leave you with a second variation of this game to think about, okay? And we'll try to tackle that on there as well. So same idea, all right? So same idea, but instead of having 7 cards, let's have 9 cards. Same idea. So 2 of them are red, the rest are black. Same idea, right? Okay, obviously you didn't like the other game. So, but instead what we're going to do, instead of arranging them in a line, we're going to arrange them like this in a grid. 3 by 3 grid. And now the object is can you flip over 3 in a row without hitting a red card? I mean, and again, it sounds pretty good. The odds on the surface kind of think they're a bit good, but again, you kind of know, because I'm saying this, that the odds are obviously not that good. The odds I present are not that good. One question, so what kind of question can you expect on exam 3 for this regard, with this kind of question, or on the final exam? Because I'm sure you would love to know that kind of information well in advance. So for 1 year, what I've done 1 year, and I do this now as a practice problem because it was a really good question, and I figure I might as well share it. I gave essentially what are the odds in the game of Monopoly where you end up going into jail due to speeding? In order, for those of you not familiar with the game of Monopoly, what that means is that you have to roll 2 six-sided dice and have them come up the same number 3 times in a row. So the idea of Monopoly, if you roll 2 six-sided dice and they come up with the same number, you get to roll again. If that happens 3 times to you on your same turn, you then instead move directly to the jail space instead. So like the question is, what are the odds of that? What are the odds of that happening? That's the kind of question I've had. On the final exam, I've used a game that was my kid's first board game. It's a game designed for toddlers to teach them the idea of cooperation and turn taking. And it involves rolling dice. And the question is like, and that question was like, okay, in this game, designed for toddlers, how often do the players win? And of course, it's like 67% or something like that. That's one game. That's one game that I've done as a thing. So nothing too complex. Sometimes on a makeup exam, I've done like, what is the outcome for rolling something in Dungeons and Dragons? But I found that people did not like that one nearly as much as I did. Even when I presented you the rules. But I will try to keep like at least like one of these scam games in reserve for an exam or something, because people find this fun. The idea that this, figuring out what are the odds to something. And for those of you curious for what games to play at casino, 1, don't. You're going to lose money. The house always wins. Otherwise, you wouldn't have a casino. 2, don't. Seriously, the house always wins. But mathematically speaking, the game is blackjack, where the player has, if they play perfectly, they have a slight edge. If they play perfectly. And that requires knowing a lot of rules and when to split your cards, and assuming that the house hasn't changed the rules to adjust those outcomes. And I think it actually is not, it may not, no, I don't know if it's better than even odds of winning that game then. But I do know when you then use card counting, then it becomes a way, that piles directly into the players. Not illegal to card count, but if you're detected doing that, you might be very politely and forcibly asked to leave, or they might just send somebody over to distract you from whatever you're doing. So gambling, don't do it. It's an easy way to lose money. Very easy way to lose money. All right. So that's it. We will talk about approximating pi again, for the second time this semester on Thursday, but we're going to do it in a very interesting way. And then on Friday, and then also on Thursday, we will go over these 2 games that I presented to you.
Hey, I demoed this lab, but it says on my campus that so I'm just here to do lab 2.
Oh, did you demo it? Well, if you said you demo it.
I'm pretty sure I did. I remember